All right. So the next topic that I want to talk about is, you know, how data communication happens using IP addresses, using IP address and MAC address both, because we're talking about the network which is Ethernet, right? So Ethernet based networks. When you think about, we would need two addresses always, which is IP and MAC, and based on that, your communication would happen. So let's say that I have, you know, uh, two devices. So this is my PCA, and I've got another PC over here. Say I've taken a proper Ethernet cable type to connect it in the proper format. So imagine this is my PCA. This is PCB. Now, the very first thing that you need to think is, you have to go to the network adapters of both these PCs and assign a respective IP address, right? So they want to exchange some type of data between them, right? Whatever type of data that they want to exchange. Your data can be of, multiple types. Very simple it is. We can have a clear text data, or we can have voice-based data, or we can have, video-based data, right? So whatever data that we are going to send, either clear text, voice, or video between these two PCs, what we need at a bare minimum is an IP address, right? So we have to go and assign this particular PCs, say an IP address. Say we assign an IP address from class A. I say 10.1.1.1, and accordingly the mask could be 255.0.0.0. So I have to go to the network adapter of PCA and assign an IP address and a subnet mask. Similarly, I have to go to the adapter of PCB and assign an IP address of, let us say, from the same network. I'm giving the second IP as 10.1.1.2, and I'm giving the mask of 255.0.0.0. So once I do that, you know that every network adapter, what we have over here, so we are assigning the IP address to the NIC of both these PCs, right? So this NIC will have, a physical address, a MAC address. So imagine that, this PC has got a MAC address, which is, normally it will be in, 48 bits, but I'll just write the first four values over here. So let's say it is like that. So what, quadruple A, all are quadruple A as the MAC address. Okay. Similarly, the MAC of this particular PC, say it is quadruple B. This is how the MAC address will look like. Sometimes it is separated by dot, or sometimes it is done using a hyphen. All right. Now, the moment you assign an IP address and a mask, so basically the MAC address is called as a physical address, the IPs and the mask are called as a logical address. So moment you assign an IP address and a mask to a particular PC, okay, the very first thing what the PC would do is, let me write it down for you guys. You assign an IP address and a mask to this PC, assign IP and mask to this PC. The moment you assign an IP address and a mask to any device, not only a PC, but any device, you assign an IP address and a mask, that device, it performs one operation called as binary ending. It's a very, very important operation. It does an operation called as binary ending. What does it mean is, it will the PC automatically would convert this IP address values into binary and the mask values into binary, and in case of engineering logic is multiplication, right? And means multiplication. So we'll take out the binary of 10. So binary of 10 is basically 1010. So it is like 8421. So it is the first four bits are 0. Then it is 1010, and the binary of ones, all the 7 bits will be 0 and followed by the last bit as 1. So likewise, this is the binary representation of my IP address 10.1.1.1, right? And the mask of 255.0.0.0, it means all my 8 bits in the first octet is high, followed by all the bits here it is 0, all the bits here it is 0, and all the bits here it is 0. So ending means it's multiplication. So what will happen is you will get the result now. So the result is basically right, 1 multiplied by 0 is all 0 and followed by 1 0 1 0. Anything multiplied by 0 will be 0 itself. So this is all 0 in 8 bits. This is again, all 0 in 8 bits. This is again all 0 in 8 bits. So the answer is when you convert it back to your decimal number. So each octet value, when you convert it back to your decimal number, you get the answer as 10.0.0.0, right? So get the logic what you got. So you have assigned an IP address and a mask to a PC. The PC automatically does, or any device, not only a PC, any device, when you assign a IP address and a mask value, the device would do binary ending. Okay, so it will convert the binary of, the corresponding decimal numbers into binary of IP and mask and multiply the value and it will get an answer. This answer is basically what it got is a network address. So the result that you get after doing binary ending, it is basically a network address. So the PC understands that, okay, based on this IP and the mask combination, my network address for this is 10.0.0.0. So this IP and this mask belongs to this network. And based on this, mask value, that means the first octet is in the network part and the remaining octets are in the host part, right? So it knows that, the first octet, this value is in the network part and the next is the host part. So the PC automatically knows using binary ending two important things. The first important thing it knows is to which network address, this PC is belonging. It says that, okay, I belong to this network 10.0.0.0, and automatically you can also say it is, in /8, right? And the PC automatically will understand that, what are the VIP range of this network. So with which IP address it can communicate, right? From this network, what are the VIP range that we have. So the VIP range is between 10.0.0.1, right, all the way to 10.255, 255, 254, right? And also it knows that, 254. And also it knows that the last IP is the broadcast, right? It knows that. So basically by using binary ending, the PC is understanding to which network address it belongs, what are the VIP addresses it has. That means this PC knows that, any IP from this range on the remote side, the PC can be able to communicate with. So on the remote end, if I have a PCB and the PCB is having an IP address, which is anything from this IP scope, this IP range, this PC can send some traffic to them or receive some traffic from them. Data communication can happen, right? Same logic over here as well. When you go to PCB, you assign the IP address and the mask to it, does binary ending, and same logic, right? So it will also, get to know that, okay, my network address is gonna be 10.0.0.0/8, and again, my valid IP address is in the same scope itself, right? So it knows, they can communicate with each other, right? So at the end of the day, this is the very first thing that will happen, right? Now, as an administrator, right? As a network administrator, we normally do what? We normally use a command called as ping to test my, IP connectivity, to test your IP connectivity. So this is very important. So if you actually, as an administrator, if you go to a device and you ping some other, remote device and you check the IP connectivity between those devices are happening, that means you get rest assured, that your basic communication from point A to point B or between those two devices can happen, right? If your IP connectivity is there, means your data communication can happen, right? So if you go with the logic of OSI model, right? So you've got, the application layer, which generates your data. That data will normally come and talk to your, transport layer at layer 4. The layer 4 will normally talk to your, layer 3, the IP layer. So between source and the destination, if you have the layer 3 connectivity, right, which is happening at the end of the day, That means if you can test layer 3 connectivity, that means layer 3, layer 2, and layer 1, right? So if all are possible, then only your layer 3 connectivity will be possible, right? So once you send a traffic, say a ping traffic, right? So ping is basically a command. It will generate an ICMP packet. So when you give a command called as ping, it generates a traffic called as an ICMP traffic to test the connectivity between the source to the destination, right? On the process, what happens is, so ICMP is part of your, layer 3. On the process, what happens is you will check the layer 2 also and layer 1 also, right? So if your layer 3 communication is possible between the source and the destination, that means your layer 2 and layer 1 is also happening. That means whatever data you receive from the upper layer at layer 3, the data can be delivered from point A to point B, right? So as an administrator, I mean, if you send a traffic using ping and you test the connectivity is available, that means you rest assured that your data communication can happen, right? So this is one thing. The second thing that I want to talk about is a very, very important concept is, what happens when you go and do ping, right? What happens when you go and do ping? Okay, let's understand that. So I go to PCA, I go to the command prompt of PCA, all right? And on the command prompt, I said, ping the remote IP, which is say 10.1.1.2. Once I do that, what happens is, so ping is basically a command. It will generate traffic called as ICMP traffic. So ICMP is a protocol which serves the job of ping. ICMP stands for Internet Control Messaging Protocol. All right. So now what will happen is you will have right now an ICMP header which will be generated because of this command ping that you gave. The ICMP header would be generated at layer 3, right? And this ICMP header will be at layer 3, right? And then we will have the layer 2 header, which is basically the Ethernet header, which is at layer 2, will be encapsulated with your ICMP header, and then the traffic will go along the media to the destination. That is the first logic you need to understand, right? When you think about the ICMP header, there are multiple, entities present inside the ICMP header. So most of the important entities that I'll take right now, it is, the source IP and the destination IP of your packet. Okay, there are other entities also, which I will discuss later down the course. But at a very, very basic level, I mean, which information you have in the ICMP header will take that, right? So basically, this will be an echo request. We normally say that when you ping somebody, when you send ping and try to test connectivity with your remote peer, we normally say that we are sending, echo request. So we are generating an ICMP header, which is type called as echo request. Okay. We will be expecting echo reply from the remote peer. We expect that we would be getting something called as an echo reply from the remote peer, right? For my echo request, I'm going to expect that I'll get an echo reply from my remote peer. Then only I'll consider my ping is successful. So if I send you an echo request, if I don't get an echo reply, apart from that, if I get something else like request timed out, source quench, destination host unreachable, etc. So any other different messages makes me understand that my destination is not reachable. My remote peer is not reachable. All right. So very simple thing. So I'll generate an ICMP header, which is of type an echo request. Okay. So this ICMP header, so basically my echo request would be generated. Okay. And then you will add the source IP. All right. You will add the source IP of your packet. You will add the destination IP of your packet. Okay. So source IP is basically your own IP address, which is basically your 10.1.1.1. That's your source IP. Destination IP is basically the remote peer to which you are trying to send the ping traffic to. That will be your 10.1.1.2. Okay, that is a remote peer. Right now, this is your layer 3 information. So at layer 3, you know that you're sending an ICMP echo request. That's your source IP. That's your destination IP. Right now, you know that as per data communication happens. So whatever data you generate at layer 3, it will go to layer 2. At layer 2, you will add your layer 2 headers. So layer 2, you will add basically your Ethernet header. So in Ethernet header, you have got the concept of MAC address. So basically, you will add along with layer 3, you will add layer 2 header as well. So layer 2 header would be basically your source MAC, right? Source MAC and destination MAC. Okay. So source MAC is basically the PC A MAC address, which is quadruple A, starts with quadruple A, as we've seen, and the destination MAC is right now not known. So if you look into this particular computer, this computer will maintain something called as a uh, local ARP cache. I'll talk about ARP right now. So it is called as address resolution protocol cache, local ARP cache. So it will maintain the the IP and the MAC resolution values inside the cache. So inside this particular PC, it knows that it has got a local IP which is 10.1.1.1, and this MAC address is quadruple A. He knows that binding, but he does not know anything apart from that. Similarly, PCB also has got a local ARP cache. In the local ARP cache, he knows that his IP address is 10.1.1.2, and his MAC address is quadruple B, right? So the PC knows that, but apart from that, anything else is not known to the PCs yet. So now what will happen is when you send a ping traffic to somebody, you know the source IP and the destination IP, right? You know your IP, you know to which IP you're trying to ping. That's fine. And the source MAC is locally, like your MAC, you resolute that from the, I mean, you found out that from the local ARP cache, right? That 10.1.1 has got a source MAC of quadruple A, but you don't know what is the destination MAC address of 10.1.1.2. Right? If you do not know what is the destination MAC of 10.1.1.2, what we'll do is you will find out, you will try to find out that, okay, if I need to reach 10.1.1.2, what is the MAC address of that guy? Now to find out that, you will actually send something called as an ARP request, right? We normally call that as an address resolution protocol request, ARP request. So this PC will generate an ARP request. Okay. So ARP request basically will go like that. So think like very basic thing, ARP request is like, who is, let me just write down here, having some issue. Like, who is, one second. Let me take a text. So your ARP request will follow like that. I mean, what is the MAC of, what is the MAC of 10.1.1.2? Right? So basically you are asking with the ARP requests and you're trying to resolute that what is the MAC address of this IP address 10.1.1.2. And the request normally will go as a broadcast, right? The request will normally be delivered as a broadcast. Now how it happens, let me tell you here. So right now what will happen is you are going to send an ARP request. So your ARP request packet will look like that. So the ARP request packet will have a source IP, which is basically, source IP is basically your 10.1.1.1, right? You are sending an ARP request for a destination IP. The destination IP is 10.1.1.2, right? You will have a source MAC. The source MAC address is yourself, quadruple A, right? And the destination MAC basically is, the destination MAC is basically a broadcast. So you represent broadcast like, all FFFFF. So broadcast MAC is like that, right? All FFF in 48 bits. This is how your ARP request normally looks like, in your, packet structure format, right? So you are sending an ARP request from your source IP to a destination IP. Your source MAC is yourself for the destination MAC. If it is all F in 48 bits, it means it is we call that as a layer 2 broadcast, right? It is called as a layer 2 broadcast. So now what happens is this ARP request goes over the media to the PCB. PCB says, oh, I'm getting an ARP request. I see that the sender MAC address is, quadruple A. The destination MAC is broadcast. So broadcast means anybody can process this particular, frame at layer 2. Then when it checks for layer 3, it will find that the destination IP is 10.1.1.2, right? So 10.1.1.2 means the ARP request was made for this PC because he's having this IP of 10.1.1.2. Then he will give an ARP reply. Before he gives an ARP reply, he will actually cache its local, ARP, cache table. He'll say, okay, 10.1.1.1, I'm getting an ARP request from 10.1.1.1. So, I know that you are part of this MAC address. So let me write down in my cache, and then I'll give you a reply with my, info, like with my MAC info, right? So it will say that with an ARP reply, it will say, one second. Generate an ARP reply now, and the source IP would be, the source IP would be your 10.1.1.2. The destination IP would be your 10.1.1.1, Okay, the source MAC is basically the B, the MAC address of this PCB, and the destination MAC will be basically your quadruple A, right? So always remember, ARP request is a layer 2 broadcast and ARP reply is a unicast, right? So ARP request is a layer 2 broadcast and ARP reply is always a unicast. So you can see that, the reply is happening to a particular, entity. So now your PCB will give a reply to PCA, and because of which PCA will now develop its local ARP cache and find out that, okay, 10112 has got this MAC address of quadruple B. Okay, so now you remembered that, when you were trying to ping, your destination MAC was not known, because of which the PC has done an ARP request, found out the MAC address of 10112, and now this MAC address would be written over here, right? So the MAC address would be now quadruple B, right? So now your ping packet, your ICMP packet will travel from point A to point B. Okay, so you're sending an ICMP echo request from PC A to PCB, but over the process, try to understand that you have to know the MAC address. To know the MAC address, you can do an ARP request, get an ARP reply, find out the MAC, build up your local ARP cache, and then only it is possible. So once you send the ping means you're sending an echo request, right? So PCB is getting this particular echo request packet. So PCB is finding that, okay, the destination MAC is me, quadruple B, the destination IP is me, 10112. All right, and let me generate an echo reply to 10111. Okay, so for echo reply, how it will happen is, if I write down here for echo reply, this is my echo reply packet. On the right side, I'm writing my source IP of the echo reply is basically 10.1.1.2. My destination IP is 10.1.1.1. My source MAC I already know it is quadruple B, and my destination MAC it is. So I have my local ARP cache now. So I know that to reach 10111, I know that the MAC address is quadruple A. So I generate an ICMP echo reply, and this echo reply can go from PCB to PCA, and your ping will be successful. All right. So at a very, very basic level, I hope it is clear. You understand that what will happen if I give an IP address to a device, what is binary ending is all about. If I have to communicate between two PCs sitting inside the same network, right? So I can see that 10111/8, 10112/8, they're part of the same network, how the communication happens. So if I do not know the MAC address of my destination, I have to do an ARP, find out the MAC, and build my local ARP cache on both the PCs, and then only my communication can start. Let's talk simple. I've got two PC here. This is your PCA and PCB. They're plugged via a proper Ethernet media. You give an IP address here, 10111, having a default mask. Give an IP here as 10112, having a default mask. This PC is having a MAC address, which is quadruple A in 48 bits, let's say, as an example I'm giving. This PC's the MAC address is quadruple B. First thing first, when you assign an IP address and a mask, the PC will do binary ending, and the PC will know that to which network address it belongs. It belongs to 10.0.0/8 network address, and it knows that what are the VIP scope it has, so it can communicate to 10.0.0.1 all the way to 10.255, 254, right? It knows that. Same thing, this PC also knows that, okay, I belong to 10.0.0.8, and this is the VIP address that I can communicate with. Okay, now these PCs will have by default something called as local ARP cache, where it will write down the binding of your IP to MAC. So it will say that okay, my IP is 10.1.1.1 and the MAC address is quadruple A, whatever we have. Same thing, this guy will also have its local ARP cache, and this is 10.1.1.2 and the MAC address is quadruple B. Okay. Now, what is the concept? Very simple. So I want to ping and test the connectivity between PC A to PC B or vice versa, whatever. So when you say the command ping space some destination IP, okay, basically you are introducing a protocol to work for the command ping. The protocol is ICMP. This ICMP protocol, it sits at layer 3 of your OSI model or TCP/IP model, however you say, right? So for ICMP, when you give a command ping, what you're doing is you're generating ICMP echo request packet. You're generating an ICMP echo request packet. Okay, so this echo request packet would be added with source IP. The source IP of the packet would be what? 10.1.1.1, right? The packet would have a destination IP. Where you're trying to ping is 10.1.1.2, that is the destination IP. And at layer 2, this is all your layer 3 information. So you know that with respect to OSI, the packet will move down to layer 2 and it will add the layer 2 header. So basically we'll add the source MAC and the destination MAC at layer 2. The source MAC will be basically your quadruple A, right? And the destination MAC is basically unknown. As simple as that. So generating an ICMP echo request packet, you're trying to ping, but your destination MAC is unknown. So if your destination MAC is unknown, your packet cannot move to layer 1 because your layer 2, the packet is, you have not added the MAC address, right? So your packet encapsulation is failing because destination MAC you have not added, so packet will never be moved down the layer, right? So you have to know the MAC address, and then only you can send the traffic to the physical wire. So for that, what the PC will do is it will generate, since the MAC address is unknown, the PC will generate an ARP request, address resolution protocol request, to find what is the MAC of 10.1.1.2. Your ARP request would look like that. So ARP request will say my source IP is basically 10.1.1.1. My destination IP is 1 second, 10.1.1.2. My source MAC is quadruple A, and my destination MAC is basically a layer 2 broadcast, because I do not know to which MAC address I should send the traffic, right? So basically I'm generating the traffic as a layer 2 broadcast. So this ARP request will travel from PC A to PC B, right? So PC B will receive the ARP request and will say that, okay, I'm seeing the ARP request. The layer 2 is a broadcast, means anybody can process it. When the PC looks for at layer 3, the PC finds his IP address over here, which is 10.1.1.2. So he knows that the ARP request was made for him, and then it will do what? It will give ARP response. So now the PCB will generate an ARP response. Before that, he got the ARP request, right? So that ARP request, because of the ARP request, the PC will know that, okay, 10.1.1 has got a MAC address of quadruple A, and that MAC address he will write it down in the local ARP cache. And then he will give a ARP response. In the ARP response, he will write down, in the ARP response packet, he will write down that, okay, source IP is 10.1.1.2, that's me. Destination IP is 10.1.1.1. Source MAC is myself, okay, and the destination MAC will be unicast, which is that quadruple A guy, right? So always remember the ARP request is a broadcast, layer 2 broadcast, and the ARP response is a layer 2 unicast. Okay, so you get an ARP response. When you get an ARP response, what happens here? your PC A says that, oh, I know that this MAC address for 10112 is quadruple B, right? Now remember your destination MAC was unknown here. So now what will happen is this PC will now, get to know what is the destination MAC, and the destination MAC will be filled up with the, MAC address of quadruple B, and then this ICMP request can be sent to PCP. Once PCP receives the ICMP request, he will do what? He will check that the ICMP request was made for its own MAC address, the destination IP is matching with his own IP, then he will generate an ICMP echo reply, right? So this PC will now generate an ICMP echo reply, right? So this packet would look like the source IP would be 10.1.1.2, destination IP would be 10.1.1.1. At layer 2, the source MAC address would be quadruple B, and the destination MAC address would be quadruple A. Now, how does it know the MAC addresses? Very simple. It knows the MAC address from the local out cache. It knows that, okay, my MAC address is quadruple B. My remote where I'm trying to give a reply, his MAC address is quadruple A. Now the ICMP echo reply will go from B to A, and A will receive the ICMP echo reply, which means the ping is successful. Very simple. So now let us say if I need to communicate between two devices which is not in the same network, then I would need something called as routing. As simple as that. So if let us say I've got here something which is say different IP here. So say not this IP, right? So I've got a different IP say over here. Imagine I've got say 20.1.1.2 over here. Imagine, and this is the mask which I have. So in this scene, what is happening is this network is different, right? So this network is 20.0.0.0/8. So even his conditions are different. So this is 10.series network, that is 20.series network. So your communication would by default not happen between two separate networks. Okay. So in that case, if I need to communicate between two separate networks, I need the concept of routing.